Hi there everybody, welcome to another Chem Complete episode, and we are going to be continuing our lecture on chemical kinetics today. So this specific lecture is going to deal with relating reactant concentration to time, and we're going to take a look at it primarily through a graphical perspective most of the time. So we will relate the math back to that, especially when we get into our slope equations and we have a y equals mx plus b. We want to tie that into kinetics so that we could utilize it in a linear format if we wanted to develop slope equations. So when we get ready to deal with this, we're going to take a look at a couple different scenarios here. The first will be for a first order reaction. That's what we're going to take a look at first. And then we will also take a look at second order and then finally at zeroth order reaction, which we did talk about somewhat in the last lecture. So for first order reactions, how can we relate time to concentration, and specifically as we're looking at a change in concentration over time for 2 points? So it turns out that these can be related through a natural logarithm. So if we take the ln of the concentration for A, where A is going to just be some reactant, okay, at time t, over the concentration of A at some initial time, which we'll call time 0 or time naught. And that is going to be equal to the negative constant times time. So that constant, the little k, remember, is the rate constant when we use rate laws. Okay, now we can rearrange this, so we could say, or if you would like to solve for a final concentration or predict, okay, you can say that you've got the ln for the concentration of reactant A at a given final time, and that is going to be equal to negative constant times time plus the natural logarithm of A naught. Okay, now the reason I also wanted to put it into this format is that this more accurately or closely represents what we would consider to be a slope equation when it's in this format, right? So this could be y, where we're talking about the final concentration or the natural log of that, right? And then Rm is the negative rate constant here, and t could be the x value. And then we could have the ln of the initial concentration being the b, right? So y equals mx plus b. Y is the concentration at final time. The negative rate constant is the slope, and keeping in mind a negative slope should be starting high and going downwards on the trajectory for a linear path. The x is going to be t, and then the y-intercept, or b, is going to be the initial concentration. Right? So when we take a look at this, and we would actually attempt to graph it, what we can do is say, let's create a graphical format, and on the one axis we will have the ln for the concentration of A at time t, and then down here we will simply have t. Okay? And what we would expect is a general slope that looks something like that. Now, forgive my tablet pen, that should be as straight as possible when we're talking about a linear relationship here. Okay. But what's important to note is that the slope in this case is going to be equal to negative k, and it is negative when you look at the shape that it's in. So anytime you're graphing this, you should see it on that downward slope. Okay. So, and again, why negative? Because A is going to decrease over time, right? So we start with some concentration of A, and then we would expect that over time A is going to be decreasing if it's a reactant. So that's a way that we can sort of tie that together. Okay, so let's take a look at an actual mathematical calculation for a first order reaction like this. So again, let's do a setup where we've got a graphical representation, and we've got a line that's coming down through here, right? And we've got over here the ln of A t, and down here we've got t. Okay, so we're going to pick out 2 points. So let's pick out 2 random points, and the values that we're going to assign to these points, we'll say that this first one up here is going to be 400 seconds, right? And it will be an ln of A equal to negative 0.34. Okay, and then we come down and we find a second point here. We'll say that this is at 2,430 seconds, and at this point the value is negative 1.50 for the ln of A. So I can find negative k, since negative k is the slope. Okay, I can find the rate constant doing this by setting it equal to change in y over change in x, right? Rise over run. So if I take a look at this, the y value would be negative 1.50 minus a minus 0.34, and that would be over the x, and the x here is going to be the 2,430 seconds minus the 400 seconds. So if you solve for that, you're going to find that it equals negative 5.7 times 10 to the minus fourth, right? And when we have that, that's equal to negative k, so then the rate constant itself, k, we ditch the negatives, and we find that k is equal to 5.7 times 10 to the negative fourth, and this is per second would be the unit here. All right, so why is this useful? Because we can measure concentration and we can measure time fairly easily in a lab. It's not easy to directly measure a rate constant. So that's something that's unique to each reaction, and we need to have ways that we can obtain a rate constant by using experimental data, and this is one way that we can do that. We can take a look at concentration, okay, and concentration change over time in order to find this value here. So that is an example of how we can use this. All right, so let's take a look at another example mathematically without the graph. So there is an organic compound which is known as cyclopropane. It is a three-membered carbon ring. It's a bunch of CH2s that are connected together. Okay, and because of the bond angle, it's a triangle, so it's got these 60-degree bond angles. This is not optimal. The optimal bond angle is 109.5 degrees. So it will very readily, in first-order kinetics, break itself down into this material right here that is open-chained in order to alleviate the bond angles. Okay, now, the rate constant for this reaction, because it's been studied, is known to be 6.7 times 10 to the negative fourth per second. So here's the question. If cyclopropane is initially at 0.25 molarity, okay? So we're going to take the concentration, we're going to say that A naught, in this case, for cyclopropane, is going to be equal to 0.25 molarity. Then the question is, what would be the concentration after 8.8 minutes? Okay, so we have 8.8 minutes, and then the question is, what would be the concentration of the cyclopropane after that 8.8 minutes? And we're calling time t 8.8 minutes from the start of this rearrangement reaction. Right? So in order to do that, we can go back up and use it in the slope format. And what we would do is say, all right, I've got the ln concentration of A at t. That's what I want to figure out. And I need to set that equal to these various values. So it was negative k, if I go back and I look at the equation. So negative 6.7 times 10 to the negative fourth per second, okay, times t. Now t, we're going to have to figure out what that is in seconds. So we take 8.8, and there's 60 seconds to a minute, so I would need to take 8.8 times 60, okay, and we end up with 528 seconds. And again, this is the rate constant is in per second, so we need to keep it in seconds. So 528 seconds. Okay, so there's the t. And then the intercept part, which would be the plus ln of 0.25 molarity. Okay, so if you go ahead and you start condensing this, I would suggest that you solve everything over here. And what you're going to end up with is that the natural logarithm of the cyclopropane at time t is equal to negative 1.74. So what's the actual concentration? Again, we have to get out of natural logarithm. So we can do that by setting the concentration at time 528 seconds equal to e raised to the negative 1.74. And if you solve for that, you get 0.18 molarity. All right. So that pretty much covers most of the first order reactions as we're dealing with this in a graphical or slope type of format. Very useful as far as actual data from a lab and being able to graph it to find rate constants. Hey, one other thing I want to mention, because this does come into play with kinetics often, is the idea of half-life. So half-life is going to be the amount of time that it takes for half of a given compound to disappear, react, whatever you want to call it. So many times half-life is referred to in relation to pharmaceuticals, drugs, or something else that's going to break down in the body, because a lot of times when you do clinical trials, they need to know how long it takes to actually expel this material that's gone into your body, and so they'll talk about half-life. We also talk about half-life a lot with radioactive dating and radioactive decay. If you start getting into nuclear chemistry, how long can a certain unstable isotope last before it has more than halfway converted over into some other stabler form? Okay, so half-life is going to be different for the types of orders that we have. So in the case of a first order reaction, the half-life equation is T 1/2, meaning that'll be the time for half of the concentration to leave. Remember, it's not half time, it is the amount of time for half the concentration to dissipate. And for a first order reaction, T half is going to be 0.693 over the rate constant K. So this will obviously change for each individual reaction, given that K changes for each reaction when we're talking about the rate constant. But it is a pretty straightforward format as far as determining half-life here. All right, so that's going to cover first order reactions. Now we're going to go ahead and take a look at second order reactions. So for a second order reaction, we want to do a similar sort of process where we can look at second order from a slope equation and graphically, if at all possible. And in order to do that, what we want to do is take a look at how we would set that up. So it turns out that for second order reactions, we have 1 over A, okay, at time t is going to equal 1 over, so you notice this time we've got 1 over instead of just the actual values, and there is no ln that's here right now, okay, and it would be plus kt. All right, so for the second order, let's go ahead and take a look at an example here. So if we have an iodine molecule as gas plus another iodine molecule as gas, they have to come together and cooperate in order to form I2. Okay, so each of them will contribute here, and that's going to make it a second order reaction overall. Each of them contribute 1 and 1. So when we take a look at this specific reaction, we've got K equaling 7.0 times 10 to the 9th. Okay, and the unit is per molarity second. So if the initial concentration of the iodine gas is going to be equal to 0.068 molarity, how much I gas will be left after 3.5 minutes? That's what we want to find. So we have a T, we have an A naught, and we have a K here. So all we have to do is work with the equation that we have above. Okay, so the question is, what is going to be the concentration of A at time T, which is A is a general term that we use when we're doing kinetics here, but it does represent the iodine gas in this case. Okay, and we're going to set that equal to the K, so it'll be 7.0 times 10 to the 9th. Okay, and notice that that K is a very large number, which means that this is reacting very quickly, is what that's telling us. Okay, so then we're going to have 3.5 minutes. Now again, we need to get that into seconds, so I would need to multiply that times 60 seconds, right, for every 1 minute. And then I could add 1 over, and then it's the concentration value, which is 0.068 molarity. Okay, so solving for this, I want to find what 1 over the concentration of the AT is. And it turns out if you solve for that, it's 1.5 times 10 to the 12th. Now this is 1 over that value. So what I would need to do at this point is I would need to take the inverse in order to get or the reciprocal in order to get the correct value. So by doing that, right, I'm going to take this value, -1, and then I'll get AT, and it is going to be equal to 6.8 times 10 to the -13th molarity. Right? So keep in mind what this says is that this is the amount of the Ig reactant left at 3.5 minutes. And this is a very, very, very tiny concentration. And as we can see, the rate constant here is very, very, very large. There's a large amount that's going on in a molarity per each second. So essentially, there's going to be almost no reactant left after 3.5 minutes. But we can measure the amount that should be left based on the values here. Okay, so second order also has a half-time. So you can take a look at this and say the half is going to be equal to 1 over, and it is your rate constant times the A naught value. That's how you determine your half-life when you are looking at a second order reaction. All right, and then if we want to take a look at a problem like that, because we didn't do a half-life problem earlier, we could say, what is going to be the half-life, okay? So let's find half-life if, using the example above, if the reactant is 0.53 molarity at the start. So that means that A naught is equal to that. So in a case like that, it's pretty easy. All you would have to do is say, right, the T1 half in relation to this is going to be 1 over the rate constant. So the rate constant that was given was 7 times 10 to the 9th molarity second, right, times the 0.53 molarity. And what you end up with, okay, because these molarities will cancel, is you get T1 half is equal to 2.7 times 10 to the -10th seconds. All right, so let's think about what that means, right? We got a time back here. It is a very, very, very small amount of time, right? So if you think about this, it's talking about 2.7 times 10 to the minus 10th seconds. It's not even anywhere close to 1 second. So what that says is that if I start with a concentration of 0.53 molarity, that half of that concentration will be gone in that small amount of time. In other words, again, confirming this is a very, very fast reaction that we're dealing with here. All right, and then finally, just to wrap this up, because we're already close to 20 minutes here, if we get to the 0th order, when we start looking at that, okay, 0th order is going to be the following. 0 order, and it is that the concentration of A t at time t is going to be equal to negative K t plus concentration of A 0. All right, so this looks familiar. This is somewhat similar to the first order, except we don't have the natural log there at this point. Okay, that's the main difference if you're kind of scratching your head. And then the t 1/2 would be equal to the A naught, and then it would be over 2 times the rate constant. All right, so that is it. We are going to leave this lecture here as far as relating the reactant concentrations to time and how we can use that to tie into rate constant. So if you found this video useful and it was a helpful lecture, please remember to leave a like, because it really helps to boost us in the YouTube algorithm so we can create more quality content for you as you undergo your studies during the semester. And while you're undergoing your studies, you should hit the subscription button so that you're up to date. If you hit the little bell, it'll tell you anytime we release content, which we're trying to do on a very regular basis now. And as always, if you head over to chemcomplete.com, I offer very affordable tutoring services if you're struggling with chemical kinetics or any other type of chemistry. Why don't you head over there and try to contact me? We can see if we can work something out. I also have guides available for sale on some of the more complicated issues that people run into with chemistry. So it's a great way to support the channel. And as always, you guys are supporting the channel just by watching my content. So thank you very much for taking the time to learn with us, and I will see everybody for the next lecture.